Hey guys, thanks for being here. I'm Srishti and I'll be presenting this with Mihika. So, before we begin, I want you all to take a look at this beautiful image. Now, what does this look like to you at the first glance? At first, it looks like a rose, but it is actually two galaxies interacting really far away. And the crazy part is that the light from this left those galaxies hundreds of millions of years ago. So when we look at something like this, we're not just seeing far away, but we're also seeing back in time. And that is why telescopes are kind of like time machines. And Hubble is one of the best examples for that. Let us see why.
This is one of the deepest optical images of the universe ever taken.
This is the full-blown Hubble Ultra Deep Field. And what's important to think about in this image is you're looking at a lot of objects in what seems like two dimensions, but really you've got a three-dimensional view of the universe.
The light from the most distant galaxies has taken billions of years to travel across the universe and reach Hubble. By taking this picture, Hubble was literally looking back in time to see the very early universe.
First thing you're going to see down here on the right-hand side, there is a galaxy very much like the Milky Way. That galaxy is about 5 billion light years away. So we're looking back in time by 5 billion years. But if we go farther back in time, 9 billion years into the past, you see this little group of galaxies, particularly these two in the center, they are odd shaped because they haven't yet had time to build these beautiful structures that we see. These are colliding together, and that's how galaxies built up to become what they see today. Even farther back in time to 12.6 billion light years, and what we see is this little red galaxy beginning to emerge. It's red because we're looking at a galaxy whose light was emitted when the universe was about 10% of its present age. And it doesn't look like an elliptical galaxy, and it doesn't look like a spiral galaxy. This is a piece of the universe that hasn't yet had time to come together with other pieces to create the spiral and elliptical galaxies we see today.
Hubble had looked back in time towards the final frontier, the dawn of galaxies. It had captured almost 13 billion years of history in a single image.
So, how does a telescope like Hubble actually capture images like the ones we just saw? Astronomy is really just about one thing: collecting light. And the better we do that, the more we understand what's out there. But light is a bit weird. It doesn't behave in just one way. Sometimes it acts like a wave and sometimes it acts like a particle. And both of these affect how we see from the telescope. The wave nature of light decides how sharp we see, and the particle nature decides how much we can detect. So now let's start with the wave part. When light travels, it doesn't go perfectly straight. It spreads out, and that is called diffraction. And this is the reason why stars don't look like points in telescopes. They turn into tiny blurry spots called airy disks, as we can see on the screen as well. If two stars are close enough, those blobs start merging and suddenly you can't tell them apart. So the real question is, how close is too close? And that's what the Rayleigh criterion tells us. The equation that we see on the screen, that theta is approximately equal to 1.22 lambda by d. So lambda is the resolution. Theta is the resolution. The smaller the theta, the better is the precision. And for that, we need a bigger diameter. So basically, bigger telescopes give us sharper images. Light also comes as particles called photons. Now, when a photon hits a CCD, it knocks out an electron, which is also called the photoelectric effect. And this is exactly how we record light. So, the wave part is what blurs things, but the particle part is what actually gives us the data. And that leads to two limits, one on sharpness and one on how much signal we can collect. So basically, telescopes are always juggling both, resolving detail and gathering enough light to make the images usable. The multi-wavelength universe. So far, we have been talking about light as if it's just one thing, but visible light is only a tiny part of the electromagnetic spectrum. Different wavelengths reveal different aspects of the universe. Now, as we all know, this is the electromagnetic spectrum. On one end are the long wavelengths, and on the other end, there are the short wavelengths. As wavelengths decrease, the energy increases. Different wavelengths produce different physical processes, and now we'll be seeing that in detail shortly. But the first question that arises is, why do we need to leave the Earth to observe space? If a telescope just collects light, then why not just keep them on the ground? So there are two main reasons for this. The first is the Earth's atmosphere. Air heats up, cools down, and basically moves along a lot. So due to this, the light gets distorted before it even reaches us and blurs the images. We can fix that partly with adaptive optics, but not perfectly. So another fix is escaping the atmosphere completely. Now, the second reason to leave Earth is that the atmosphere actually blocks out a lot of light. We only get visible light, some infrared, and radio. The light that is ultraviolet, X rays, gamma rays, they never make it past the atmosphere. And although this is great news for the life on Earth, it is not so great for astronomy. And that is why we need to send the telescopes to space. Now, as I had already told before, every wavelength tells us something different. And we'll be learning all of this in detail now. So, gamma rays and X rays. The image that we see is a Crab nebula seen in X rays by Chandra. These wavelengths come from extreme environments, so black holes, supernova explosions, and neutron stars crashing into each other. So, if visible light shows us what the universe looks like, then we can say that X rays show us where it gets violent. The ultraviolet. The image that we see is Orion Nebula captured by Hubble. UV helps us study hot, young, and massive stars, basically the stars that are in their early and energetic stages. They shine really strongly in ultraviolet, and that is why it is perfect for us to study how stars are born and evolve. Visible light. The images that we see on screen, this is the same object but in different wavelengths. Now, what differences do you notice in this? Would anyone like to say? Just any basic difference? Yes, go on.
The second image is more sharp than the first.
Yeah, yeah, we can say that we are observing a lot more stars in the background in the infrared image, right? So basically, what is happening is in the visible light, a lot of that detail is missing that we can see in the infrared. The top is the visible and the bottom is the infrared, by the way. So what is happening is that in the visible light, the dark dust clouds block the view of many stars because visible light gets scattered by these dust particles. Visible light has shorter wavelength. It gets scattered and then it doesn't pass through the dust clouds. But infrared has longer wavelengths and so it can pass through the dust much more easily. And that is why we can see these stars and structures that were actually hidden in the visible image when we actually use infrared telescopes. Now, as we had already seen, infrared astronomy lets us through cosmic dust. It also helps us study stars forming inside dense molecular clouds and detect cool objects like brown dwarfs and exoplanets, and also observe some of the earliest galaxies in the universe. Now have a look at this image. This is nicknamed the penguin and the egg. And I found it to be a really interesting comparison. The image on the right was taken by Hubble in visible light, and the image on the left was taken by Webb in near infrared light. Now, in the Hubble image in visible light, the dark dust lane blocks our view of many stars. And we can even see a faint bridge of material connecting the two galaxies as they interact. So, exactly the same reason that the visible light gets scattered due to dust, and that's why uh, we can see the differences. Now, one more interesting observation is have a look at the top right. We can see those two bright stars, and notice how the stars themselves look different, the number of spikes in them. Now, we'll be coming back to this shortly, but just take a note of that. Radio waves. These let us see cold hydrogen clouds, jets from galaxies, and even leftover light from the Big Bang. So the question arises that if all these wavelengths are just light, then why can't we just send one telescope to observe all of them? And the answer is simple because different wavelengths require completely different detectors and telescope designs. So instead of just one telescope, we've built specialized observatories for different part of the spectrum. So there are four great observatories that NASA has launched. And there's a fun fact that many of NASA's major space observatories are named after famous scientists. So one we can recognize from here is Chandra, which is named after Subramaniam Chandrasekhar. Now the Hubble observes visible light, Spitzer observes infrared, Chandra observes X-rays, and Compton observes gamma rays. And together these four observatories gave us something that no single telescope ever could, which is a view of the universe across the entire EM spectrum. So a question that we all have had at some point is how do telescopes record wavelengths that we cannot see? We have seen all these images. Even previously, we have seen that there were images of infrared, but that is not in our visible spectrum. So why can we see the colors? So the answer is that scientists color these images because even when we cannot see the wavelengths with our eyes, we still need to make sense of the data, right? So they assign colors to different wavelengths. And sometimes the color do follow the wavelengths. So shorter wavelengths like violet are mapped to blue, and longer wavelengths like infrared will get mapped to red. But it is not exactly a fixed rule. Like scientists choose the color mapping to make the features easier to be seen. It's more about highlighting the data than literally matching any real color. So yeah, basically that is what it is. The raw data that we see in a telescope is black and white only, and the brighter pixels represent more light. And as I said, blue shorter wavelengths and red sometimes maps longer wavelengths, but it is not a rule. All the colors represent real physical information that are captured by the CCDs. Now, whether we are looking at visible light, infrared, or X rays, the goal is always the same. We have to turn light into information. But getting to this point didn't really happen overnight. And to see how these telescopes have evolved, I'll be handing it over to Mihika.
So, what is the history of the telescope? And who was the first person to actually point one at the night sky? And how far have we come from that one night? To answer that, we'll have to go back in time. It all started some 400 years ago in a spectacle maker's shop in Netherlands. The year is 1608. Hans Lippershey realizes that if you line up two glass lenses in a tube, distant objects appear right in front of you, going up to 4 times in magnification. This was the birth of the refractor telescope. Refractors use a very large objective lens in the front to gather light and an eyepiece at the back to magnify it. Although these weren't called telescopes just yet. At first, the military and pirates were the only ones using them. Nobody had yet thought to point them up. And no, the first one to do so was not Galileo, although this is the telescope which Galileo made. But a month before Galileo, an Englishman named Thomas Harriot secretly mapped the moon. But Galileo was the first to make his findings public. The images shown here are sketches Galileo made himself of his observations. He built his own powerful refractor, going up to 30 times in magnification. He pointed at the sky and shattered the whole view. He saw craters and mountains in the moon, proving that heavens weren't perfectly smooth. He looked at the Milky Way and realized it was made of countless stars. And most importantly, as you can see in the image on the left, he found moons orbiting Jupiter. This provided hard evidence that Earth was not the center of the universe. It is surprising how all of this is just some 400 years ago. But the early glass lenses had a major flaw. They created blurry, rainbow colored halo around objects, as you can see in the left. This is because the lens acts like a prism and splits the light into its constituents. Because of the different wavelengths, each of the colors has a different focal length, so a sharp image cannot be formed. This is called chromatic aberration. We will look at this in detail later. In the 17th century, Isaac Newton decided to fix this. He swapped the glass lens for a curved mirror, inventing the reflector telescope. The primary mirror collects light and bounces it to the secondary mirror. This sends the light to your eye. Mirrors don't bend light like lenses do, meaning no more of that rainbow colored halo. Plus, it is much easier to build massive mirrors than massive lenses, allowing astronomers to collect way more light for better observations easily. And the shape of the mirror matters too. At first, we have parabolic telescopes. These are shaped like a parabola and are amazing at converging all the incoming light to a single sharp focal point. They eliminate spherical aberration, or the blurriness, giving us razor sharp images. There are also elliptical telescopes. They are way more compact and are more preferred nowadays. They offer a much wider field of view. They are perfect for taking panoramic shots of massive galaxies and star clusters. Here are a couple examples of parabolic telescopes. On top, we have the 500-meter aperture spherical radio telescope, or FAST. It is a radio telescope located in southwest China. It consists of a 500-meter diameter dish constructed in a natural depression in the landscape. It is the world's largest filled aperture radio telescope. On the bottom is probably one of the most famous radio telescopes in the world, Very Large Array. It uses 27 Cassegrain antennas, each 25 meters in diameter, that can be moved along a Y-shaped rail system. Ellipsoid telescopes utilize grazing incidence to focus high-energy light, like X-rays. Traditional telescopes fail at these wavelengths because high-energy photons pass straight through glass rather than reflecting. Grazing incidence forces the light to bounce off metal at shallow angles. Eventually, we realized that we could combine the sharp lenses of Galileo with the powerful mirrors of Newton. This gave us compound telescopes, like the Schmidt-Cassegrain. Light passes through a collector lens at the front, bounces off a primary mirror at the back, and reflects again off a secondary mirror. It literally folds the path of light inside the tube. This gives astronomers huge light gathering power in a very compact portable package. By the 19th century, we weren't just looking at the shape of the stars. We started analyzing the light. By passing starlight through a spectroscope, we could break it into a rainbow, sort of a barcode. By analyzing its emission spectrum and the absorption spectrum, we can comment on its composition. And here is how.
When we see pictures of distant heavenly objects, how do scientists make conclusions about their chemical composition? This is because of something called spectroscopy. You see, different elements when exposed to heat or some kind of electrical agitation emit characteristic wavelengths. This is because atoms are made up of a nucleus surrounded by electrons and fixed energy levels. When an electron jumps from a higher energy level to a lower energy level, a specific frequency of light is emitted and vice versa for absorption. So if you take a look at an element like hydrogen, it has a signature wavelengths both in the visible spectrum and beyond it for all possible electronic transitions. Take a different element like iron and you get a completely different spectrum associated with its own energy levels. So each element in the periodic table has its own unique absorption or emission spectra. Now take a look at the light coming from the sun. You can make its comparison to all the emission and absorption spectra of known elements and get an idea about its chemical composition. This is how we know the chemical composition of distant faraway objects, because atomic physics is the same everywhere.
But ground telescopes have a huge problem, the Earth's atmosphere, and you've seen this before. So what is the solution? It's simple, leave the atmosphere. In 1990, NASA and the European Space Agency, ESA, launched the Hubble Space Telescope. Deployed by the Space Shuttle Discovery, Hubble orbits above the atmospheric distortion. Free from the twinkling air, it gives us an image with exceptional clarity. Hubble helped us figure out the exact age and size of the universe, investigated black holes, and gave us a first real clue about dark matter and dark energy. The video we saw in the very beginning was of the greatest space images ever taken. And there is actually a very interesting story behind it. The scientists decided to point the telescope to a point in the sky with no yet detected observations. Just a single dark patch in the sky, no longer than a rice grain, for 10 days straight, and collect the observations. And this is what we got, the Hubble Deep Field. And lastly, we have the James Webb Telescope. It is designed to blow past Hubble's limits by looking in the infrared spectrum. Because the universe is expanding, light from the earliest galaxies stretches into infrared before it reaches us. We have seen a few examples before, and this is another. This is the pillars of creation, a dense column of interstellar gas and dust. To the left is the image taken by Hubble, and to the right is the one by James Webb. It uses near infrared camera to pierce through the thick dust. This allows astronomers to see straight into the pillars, revealing hundreds of newly formed, actively blazing stars that were previously hidden from the view. But whether you have a reflector, or a compound telescope, it is useless if you can't aim it. There are two types of mounts we can use. First is the azimuthal, or the Altaz mount. This is like a camera tripod. It moves up and down, which is the altitude, and left and right, which is the azimuth. It is intuitive, easy to set up, and perfect for beginners. Then there is also the equatorial mount. As the Earth rotates, the stars appear to drift across the sky. An equatorial mount has an axis perfectly aligned with the Earth's celestial pole. We do this by pointing it to the Polaris, or the North Star. It is an absolute must for astrophotography where long exposure shots are needed. This is a little difficult to visualize, so we'll look at a couple of simulations. To track a star with the Altair mount, we have to rotate the telescope about both the axes, the altitude and the azimuth, as you can see here. However, for the equatorial mount, we only have to turn one knob around to smoothly track a galaxy across the sky all night. Now, I will hand over to Srishti to explain how exactly these telescopes capture these beautiful images.
Hey guys, so we have spent most of this talk looking at what telescopes reveal about the universe. Now it's finally time to investigate the telescope itself. Every telescope image contains clues, not just about distant galaxies, but also about the very instrument that captured them. And today's mystery is, why do stars in telescope images sometimes have these spikes, as we can see in the image? These spikes appear to be a part of the star itself, but they aren't. Somewhere inside the telescope, something is creating them. And our objective is simple. We have to identify the source of these spikes. Now let's take a look at the suspects. The aperture. The aperture is the diameter of the telescope's primary light gathering element. It basically determines how much light enters the telescope. And as we had seen before, a larger aperture collects more photons and it basically improves image quality. And it also improves resolving power. The focal length. Longer focal length means higher magnification and so a smaller field of view, which is perfect for fine planetary detail. But a short focal length gives a wider field of view and it is essential for surveying large regions of the night sky. Spider veins. These are the support structure that hold the secondary mirror. These are found in all reflecting telescopes. They are positioned directly in the path of the light, which makes them suspicious to our star analogy. The forensic challenges. Before identifying the culprit, we need to understand how light exactly behaves inside a telescope. So let's start with diffraction. When light behaves as a wave and it passes through an aperture, it spreads out. And as a result, stars appear as airy disks rather than infinitely small points. And diffraction sets a fundamental limit on resolution, as we had seen earlier. This is the Rayleigh's criteria. Chromatic aberration. If you observe in the image on the top, there is a halo effect, blue and red halos around stars. And on the image at the bottom, we can see that there is a yellow tint near the moon's edge. This effect is called chromatic aberration. It occurs because different wavelengths of light refract by different amounts when passing through a lens. As a result, these different colors focus at slightly different positions. Instead of a sharp image, we get colored fringes and reduced clarity. Now, refracting telescopes correct this using achromatic doublets or apochromatic triplets. Reflecting telescopes avoid this problem entirely because instead of lenses, they use mirrors. The evidence log. Now that we've examined the telescope's components, let's look at the qualities that astronomers use to evaluate telescope performance. The Plates scale. The plate scale tells us how much of the sky corresponds to each pixel on the detector. So, smaller plate scale means higher magnification and more detail. A larger plate scale means wider field of view and better sky coverage. We can also relate this to the focal length that we had seen earlier. The focal ratio. This basically tells us how quickly a telescope can collect light. A low f ratio, like f by 4, gives faster imaging. It is better for faint galaxies. And a high f ratio, like f by 10, it is great for better image scale. And basically, a lower f ratio allows the detector to reach a given brightness level more quickly. The precision factor. Large mirrors alone do not guarantee good images. So optical surfaces must be polished to extraordinary precision because even tiny imperfections can reduce sharpness, lower contrast, and distort fine details. A telescope is only as good as the quality of its optics. So now let's return to the case. We have understood aperture, focal length, diffraction, and now it's time to return to the mystery that why these stars have spikes. The evidence that we've collected so far is that the spikes are not a part of the stars. The diffraction creates patterns in images, and the spider veins sit directly in the light path. So our primary suspect is the spider veins. But there's an unexpected evidence. Yeah, we've already found that support veins obstruct light, and yeah, that is the reason why we have spikes in stars. But if you remember the penguin and the egg image that we had seen earlier, this is what it is. The number of veins in spider's veins decide the number of spikes. So basically, if there are 3 veins, then there will be 6 spikes. 4 veins, then there will be 8 spikes. And as they are overlapping, the resultant is only 4 spikes, but actually there should be 8. Like you get it. So the Hubble has 4 veins and the star spikes are 4. But the James Webb telescope has 3 veins, but the star spikes are 8. If you look closely, you can also see this horizontal line. So there are 8 spikes. These are both images of the penguin and the egg that we had seen earlier. So basically, why is that? We'll be seeing very soon. Because this can't be just because of the veins. There is something else contributing. As I just said, there are 8 spikes. This is the image, a closer look at the image. The JWST's primary mirror consists of 18 hexagonal segments. A hexagon contains 3 pairs of parallel edges, and these edges also create diffraction patterns. And due to this, the hexagonal mirror uh, contributes to 6 spikes, and also the spider veins contribute to 6 spikes. And these overlap in such a manner that we get a resultant of 8 spikes, as we'll be seeing in this image. Yeah, the segmented mirror and the spider veins both contribute, and finally we get an 8-point pattern. So the case is closed. Every telescope leaves fingerprints on the images it creates. So understanding the telescopes basically helps us understand the image as well. Now that we understand aperture, let's take a look at the GTC. With a 10.4-meter diameter, it is the largest operating single aperture optical telescope. Instead of a single mirror, it uses 36 hexagonal segments acting as just one surface. As we can see in the equation, light collection scales with area, that is d square, ds diameter. So compared to a 5-meter telescope, the GTC collects about 4 times more light, and it reveals fainter objects and finer details. The extremely large telescope is being built by the European Southern Observatory, and this pushes this concept even further. Its 39.3-meter primary mirror will make it the largest optical and near-infrared telescope ever built. It will collect vastly more light than any current telescope. And this is the major leap in ground-based astronomy. So let's have a look. This is truly an ambitious project.
From ESO's Paranal Observatory, Cerro Aramazones will be home to the EELT, one of the next generation of enormous telescopes. A main mirror 39 meters across and a protective dome almost 80 meters high will make this one of the biggest astronomical projects ever undertaken. Truly an extremely large telescope. The EELT is, like all big astronomical telescopes, a reflecting telescope. Mirrors are key to its operation, and there are 5 of them in total. By bouncing the light from one mirror to another, it's possible to make the telescope relatively compact. Without this series of mirrors to fold the light beam, the telescope would be even bigger. The mirrors can also be used to make adjustments that result in the best images possible. The main mirror is segmented and is made up of 798 individual elements, which together add up to a reflecting surface 39 meters across.
Revolutionizing the cosmos. Collecting light is only a part of the problem. The real challenge starts with recording it. For centuries, astronomers relied on the human eye, but it cannot store information. Light detectors like CCDs have changed the game. A CCD is a grid of pixels that converts incoming photons into electric charge. Each pixel accumulates charge over time, which is then read out and digitalized. To reduce interference from thermal electrons, CCDs are cooled to around minus 100 degrees Celsius. Photons interacting with silicon can free electrons via the photoelectric effect. This charge directly represents light intensity across the image. The quantum efficiency describes the detector effectiveness, and it is typically above 90% in modern CCDs. So basically, CCDs capture nearly every photon that hits them. Basics of digital imaging. Raw telescope output is usually a noisy grayscale signal rather than a finished image. The goal is to separate consistent astronomical signal from random noise introduced by electronics and the detector. As you can see, the goal is to increase the signal to noise ratio. The signal is the light that we get from the stars, and it is constant, but there is noise generated by the equipment or the air around us, the difference in temperature, and so on. So that is why astronomers take long exposures, so that they can strengthen the signal while averaging out the noise. When we take so many exposures, first we stack them, then we go through with calibration and processing. We do noise reduction, color mapping, and so on, and finally reveal structure hidden in raw data, as we can see in the image on the left. We can use software like Cyril, GIMP, etc. for this workflow. And similar techniques are now common even in amateur astronomy. Today's hobbyists can use dedicated CCD cameras to achieve results that rival professional work from decades ago. This is how far we have come. And this is why telescopes act like time machines. Each image reveals deeper space and earlier cosmic history. So, with that foundation, I'll hand it over to Mihika to connect this to major space telescopes.
For most of history, much of the sky was hidden. For most of history, much of the sky was hidden, for there are many kinds of lights our eyes can't see. And despite the use of powerful technologies that made this light visible, as we have seen, the sky remained veiled because the atmosphere blocked much of the light from reaching the ground. A twinkling star is atmospheric turbulence. The Earth's air is wavy and distorted and full of gases that absorb entire chunks of the EM spectrum, like X rays and ultraviolet. So, in the mid 20th century, we decided to go out of this atmosphere to observe the universe in its entirety. By placing telescopes into orbit around the Earth, we completely bypassed the atmosphere. Out there, the view was perfectly unobstructed. Space telescopes can stare at a single galaxy 24 hours a day, 7 days a week, without ever worrying about clouds, light pollution, or even the sun coming up. But how do these machines actually work? They are essentially flying robots packed with four main systems. The optics. This is high quality mirrors that gather ancient light. The detectors, advanced CCDs, as you have seen, that convert light into digital data. The instruments, powerful spectrographs that break light apart to tell us what a star is made of. And of course, the power, giant solar panels to keep everything running, and massive antennas to beam that data back down to Earth. First, we have the Hubble Space Telescope. This revolutionized astronomy by capturing the sharpest images of a universe ever seen. Launched in 1990, its discoveries have helped scientists determine the age of the universe and uncover secrets of the distant galaxies. The scientific instruments which helped us do that were the Wide Field Camera 3. This is the Hubble's main camera, capturing ultraviolet, visible, and near infrared light to take stunning deep space images. There is also Advanced Camera for Surveys, ACS, which captures large, wide field swaths of space to study the earliest activity in the universe. And of course, Cosmic Origins Spectrograph and the Space Telescope Imaging Spectrograph. Spectrographs like these split light into individual wavelengths to determine temperature, chemical composition, and velocities of celestial objects. These are a few of the images captured by Hubble, some of which we've already seen before. But how were these images made?
Hubble houses 6 scientific instruments that observe at different wavelengths. Together, they expand our vision into infrared and ultraviolet light. That doesn't mean Hubble can show us never-before-seen colors. In fact, the telescope can only see the universe in shades of gray. Seeing in black and white allows Hubble to detect subtle differences in the light's intensity. If one wavelength is brighter than another, that tells us something about the science of that object. But because color helps humans interpret what we see, NASA specialists work to process and colorize publicly available Hubble data into more accessible images. When Hubble snaps a photo, it puts a filter in front of its detector, allowing specific wavelengths to pass through. Broadband filters let in a wide range of light. Narrowband filters are more selective, isolating light from individual elements like hydrogen, oxygen, and sulfur. Hubble observes the same object multiple times using different filters. Image processors then assign those images a color based on their filtered wavelength. The longest wavelength becomes red, medium becomes green, and the shortest blue, corresponding to the light sensors in our eyes. Combining them gives us a color image, showcasing characteristics we can't make out in black and white. Adding color reveals the underlying science in every image. It's like translating words into another language, making sure no information is lost.
Next is the Chandra X-ray Observatory. And as you've seen before, all of these are named after scientists. This was launched in 1999, designed to hunt for extreme high-energy events like exploding stars and the violent edges of the black holes. It successfully detected gravitational redshift in binary stars, proving Einstein's general theory of relativity in distant cosmic environments. The image on the top left is the supernova Cassiopeia A. Chandra mapped out the iron and heavy elements being flung outwards, rewriting theories on how massive stars explode. This is a sonograph created of it. It is to aid the visually impaired experience the wonders of the universe too. Next is the Spitzer Space Telescope, launched in 2003. It is built to see the universe in thermal infrared, piercing through thick cosmic dust clouds to see infant stars forming. The picture on the bottom right is Saturn's outermost ring discovered by Spitzer. It has a massive diameter equivalent to 300 Saturns lined up side to side, and it is thick too. About 20 Saturns could fit in its vertical height. As incredible as the previous telescopes like Hubble was, they had a limit too. For example, Hubble was built to see visible light. But remember, the universe is expanding. When the very first galaxies were made 13.5 billion years ago, they emitted visible light. But as the light traveled towards Earth, the fabric of the space itself stretched out, shifting it down to the invisible thermal infrared spectrum. To see the dawn of time, we couldn't just look harder. We needed a completely new kind of machine. And that's where the James Webb Space Telescope came in. Before looking at that in detail, I would want to show you guys a video where we can see how different the images captured by Hubble and James Webb are. So now the James Webb Space Telescope. This is an absolute engineering masterpiece, a joint collaboration between NASA, the ESA, and the Canadian Space Agency. It is so big they had to fold it up like origami just to fit it inside a rocket. Its primary mirror is a massive 6.5 meters across, and it is made up of 18 golden hexagonal segments, as we've seen. But because GWST looks for faint ancient heat, the telescope itself has to be kept unbelievably cold. Otherwise, its own body heat would blind its sensors. So, it is behind a gigantic, multi-layered sun shield, the size of a tennis court, dropping the telescope's instruments down to cryogenic temperatures, near absolute zero. But where to place this engineering marvel? The James Webb Telescope has a halo orbit around the Sun-Earth L2 Lagrange point, which was selected to optimize its infrared instruments. Lagrange points are positions in space where the gravitational forces of a two-body system, like Sun and Earth, and the centripetal force balance each other. Orbiting around L2 prevents the spacecraft from entering Earth's shadow, which allows NASA to maintain its position with minimal fuel. What is this giant golden mirror looking for, though? It has a few primary targets. The first, galaxies. It is literally acting as a time machine, trying to capture the moment first light turned on in the universe. Star and planet formation. Because infrared light pierces right through cosmic dust clouds, Webb can peek inside stellar nurseries to watch infant stars and protoplanetary disks forming. The origins of life. By analyzing the atmosphere of distant exoplanets, GWST is hunting for chemical building blocks of life, like water, methane, and carbon dioxide. This next video gives us some insight about the mission.
From a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe.
December 25th, 2021, Christmas Day for many. The largest, most powerful, and most complex space telescope ever built begins its journey into space. Six months later, its first images are released, demonstrating its incredible scientific power. Building and then launching such a large telescope into space was an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded like origami to squeeze inside the European Space Agency's 18-foot diameter rocket fairing. Once in space, unfolding Webb was an intricate ballet. For nearly 3 weeks after launch, controllers at the Space Telescope Science Institute in Baltimore stepped through the activation of 178 release mechanisms, enabling Webb's deployable pieces to carefully unfold, while also guiding Webb to its orbital destination, an orbit around Lagrange Point 2, nearly 1 million miles from Earth.
And we have a fully deployed JWST observatory.
After this delicate dance, Webb's golden mirrors were precisely aligned using motors behind each mirror segment, adjusting them to form one monolithic mirror. Science exploration started once Webb's instruments fully cooled, about 6 months after launch. Webb is designed to capture the faint infrared light from the very first galaxies to form after the Big Bang, looking back in time more than 13.5 billion years. To do this, Webb has the largest primary mirror ever flown in space. At 6.5 meters, it has more than 6 times the light collecting area of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown, a 5-layer tennis court-sized sun shield that blocks heat from the sun, Earth, and Moon. The Webb telescope was a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. And it's now being used by astronomers worldwide to tackle some of the most fundamental questions about the universe, revealing sights we've never seen before. Webb is an exploration powerhouse. With it, we can see farther back in time and explore the very first galaxies that formed after the Big Bang. We can analyze atmospheres of planets orbiting distant stars, see hidden details in planets in our own solar system, and relish the beauty of the cosmos. Webb is our eyepiece to the uncharted, unknown, and unimagined.
And the results we are getting from this telescope are already jaw-dropping. Take a look at our own cosmic background to the left. In October 22, Webb turned its golden eye towards Neptune. Before Webb, we hadn't gotten a clear look at Neptune's delicate glowing dust rings ever since Voyager 2 flyby in 1989. Webb captured them in unprecedented detail. Oh, look at the middle. This absolute wonder, Wolf-Rayet star system, WR140. This is a binary system which is two massive stars locked in a gravitational dance. Every time their orbit brings them close together, their intense stellar winds crash into each other, puffing out a massive ring of glowing dust. Webb captured 17 perfectly concentric rings. It is quite literally looking at the trees rings of a cosmic giant. It has also managed the impossibly difficult task of directly imaging exoplanets. Before Webb, we were only able to look at around 20 exoplanets. Before ending, let's look at another cool telescope, SOFIA. This is a heavily modified Boeing 747 SP aircraft equipped with a 2.7-meter reflecting telescope. Before retiring in 2022, it flew into the stratosphere up to 45,000 feet to capture infrared light that is otherwise blocked by the Earth's atmospheric water vapor. The aircraft was modified to feature a massive door in the rear fuselage that could be opened mid flight. A specially designed bulge in the fuselage redirected wind away from the telescope cavity to prevent aerodynamic turbulence and structural damage. In the end, let's look at two images. To the left is the deep field image from Hubble, and to the right is the one from James Webb. We've already improved so much, and the progress is not getting any slower. From a simple glass tube in a Dutch shop 400 years ago to a cryogenic golden mirror peering through the dust of creation. Space telescopes represent the absolute pinnacle of human curiosity. We took our most delicate, precise mirrors, strapped them to controlled explosions, and threw them into the freezing vacuum of space, just so we could finally see clearly. They don't just show us what the universe looks like, they are looking for the origins of life, the birth of stars, and the edge of time itself. And the most exciting part, we are just getting started. Thank you for joining us at Learner Space presented by Kritika. We're happy to take any further doubts that you have. Also, I had seen a doubt in the group which asked what Lagrange points the other telescopes are sent to. The ones that we discussed, Hubble and Chandra, they are low Earth orbit, so they're not sent to any Lagrange point. And the Spitzer Space Telescope, it orbits the Earth. It orbits the sun in an Earth trailing heliocentric orbit. So it's like moving away from Earth with every passing second. Are there any other doubts? Sorry, you were not audible.
Can you hear me now?
Can you drop your doubt in the chat? Your voice is not clear.
Oh, okay. Hello.
Yeah.
There is a doubt in the WhatsApp group. Please check that one first.
Okay, yeah, 1 second. No, sorry, we hadn't covered that yet, so I don't think we'll be able to answer that for you right now.
As you said earlier, that Hubble captures images in like visible light, right?
Yeah.
And do we still see some chromatic aberration or something like that occasionally in the images captured by? That or any other, lens effects?
No, actually, in the space telescopes like Hubble, there is no chromatic aberration.
Hubble is a reflecting telescope, and those don't have chromatic
Okay.
aberration.
I thought it had a lens. Okay, thank you.
Are there any other doubts, or we can end the meeting then? Okay, then thank you for joining. We will soon be sending the assignment and the submission links in the respective groups. Thank
Thanks
you.
for joining, guys, and staying.